Okay, good morning everyone. Shall we make a start? I hope you can all hear me at the back. Can you give me a wave? Wonderful. Great. So a very, very warm welcome to the Environmental Impacts of Computing in Health and Life Sciences workshop. I'm Charlotte Rae from the University of Sussex, and I'd like to thank you all for joining us today, whether that's here in the room or our colleagues online. So first, some housekeeping. We're not expecting a fire drill, so if you hear the fire alarm, there is a fire, so please proceed to the fire exit and follow the marshals. There is Wi-Fi available, welcome Wi-Fi, and via that you can access today's programme via the QR code that's on the printed programme on your tables. And if you're online, I think one of my colleagues can drop the programme into the chat for you. So today you're going to hear from me first to give you a big picture on why, as health and life scientists, we need to address the environmental impact of our computing activities. And then you'll hear from Dr. Gabrielle Samuel from King's College London on the role of the wider research infrastructure for institutions, for funders in this. Then we're very lucky to hear from Talia Kaplan at the Wellcome Trust on what Wellcome have been doing in this area. And then we'll hear from Martin Farley on the critically important LEAF scheme that I'm sure many of you will be familiar with, that is a really valuable institutional approach to embedding sustainability in research activities. So we set up this event because we felt that there was a really big knowledge gap in understanding amongst health and life scientists on the ways in which our research computing is impacting the environment, but also a gap in understanding on what we could and should do about this. Nowadays, our big data sets and our intensive analyses are using lots of energy. And this is getting us terribly exciting insights in terms of the scientific gains, but this is coming with the downside of the potential environmental consequences. So the aim of today is firstly to increase our understanding of why is this important, examine what scientists, funders, institutions are currently doing, and then look at how we can measure and assess our impacts and crucially address them. We've split the day into two main segments. So in the morning, we're going to hear a series of talks, first focusing on the big picture of why this matters and where we currently are with tackling our computing footprints as a community. And then after a coffee break, we'll get into some of the more technical details of this and exactly where our digital footprints are coming from. And we do welcome questions. What we'll do is at the end of each of these short talks, I'll ask for any short clarification questions. And then at the end of the first 4 talks, we'll ask for bigger questions that you could address to either one speaker or to a combination of us. So for those of you in the room, just feel free to put your hand up and we'll come around with roving mics. For colleagues on Zoom, if you can please type in the chat with your question. We have colleagues here moderating the chat who will be able to pick up those questions. And if I could ask you to tell us when asking that question in the chat if you would like us to read that out for you, or if you would like to read it out yourself so we can hear you. Okay, then in the afternoon we'll move towards a discussion and problem-solving activity for us to think through together what are the practical, actionable steps that we could take in our own research, and how can you take those actions back to your respective fields and communities. And we have a whole spectrum of health and life science fields represented here today, and we really wanted to bring together colleagues from different disciplines, whether that's on your tables here in the room or in breakout rooms on Zoom, so that we can take ideas and inspiration from each other. And these discussions will be moderated by the morning speakers, so you'll have one of us facilitating those discussions. And then finally, at the end of the day, we'll report back to the main room so that we can take away practical actions to make a change in our research computing practices. Okay, so I'm now going to move on to give the first talk in our section about the big picture and explain why I think the environmental impact of computing matters for health and life scientists. So, who here has seen this figure before? Hands up. Okay, great. So for those on Zoom, that was probably about 80–90% of people in the room are familiar with this figure. So of course, this is change in global temperature over the last 170 years. And what this shows is the rising global temperature that's happened just within the last few decades. And of course, as scientists, we know that this is due to increasing greenhouse gases in the atmosphere as a result of human activity. But what this figure doesn't show you is the exponential nature of that increase. So here we can see the exponential increase in carbon emissions as a result of human activity has largely happened within the span of just one human lifetime. Homo sapiens has been around for 100,000 years, but we've completely altered the biosphere of our planet in just one human lifetime. And this is almost entirely due to the burning of fossil fuels for energy generation. Now, you all know what the consequences of this are. We're increasingly at risk from natural disasters, from floods, from fires, from droughts. And this is happening in the UK and around the world. Recently, we had lots of flooding in the UK and 3 people died. So this is not something that is just affecting humans in the global south, it's affecting us here in this country too. Many of you will have had the warning last month from the UN Secretary General, Antonio Guterres, that humanity has opened the gates to hell. And we know that every domain of human activity is contributing to this and threatening our existence on the planet, because every domain of human activity is burning fossil fuels. And that includes scientific research. That exponential rise in carbon emissions and associated temperature rises mirrors exactly the exponential rise in the resources that are now being used for health and life science research. And here's an example from my own field of MRI brain scanning. You can see the exponential increase in dataset size over the last 20 years, and note the logarithmic scale on the y-axis. We've moved from 20 years ago scanning maybe 20, 30, 40 people per study to the UK Biobank now scanning 100,000 people. And this is a fantastic health and life sciences resource, and it's going to deliver, and already is delivering, so many exciting insights, but it's not sustainable. This is also mirrored in other domains of life science. So if we look at data set size in the Open European Bioinformatics Institute resource, you can see how this has grown and grown and grown over the last 15 years. And along with that data set increase, the amount of compute that we're using to analyse that data is growing and growing and growing. Here's an example from the machine learning literature in which we can see significant growth in the use of compute to train models. And again, note the exponential nature of this increase in the last few years, mirroring closely the increase in carbon emissions. So wherever you look, we're going faster and faster in using more and more resources. So where do the environmental impacts come from when we're running a health or life sciences research project? Well, first we have to acquire the data, which might involve single-use lab consumables or energy-hungry big equipment. Then we have to store the data, which, as you've seen from the MRI and bioinformatics examples, is increasingly hefty in size. And then we'll run some analysis, the really exciting part. But to do that, we need energy to power the computers. And then we might share the data in the spirit of open science, but that again has an impact because the data have to be stored publicly, usually on servers. And these final 3 stages all critically rely on server infrastructure. Racks and racks of computers in vast rooms which have to be air conditioned. And there is an energy expenditure just in the overheads of the servers if we're just storing and sharing data. But today we're going to focus in particular on that middle analysis step. And that's because of the increasingly heavy compute that is required nowadays to analyse these big data sets. And you'll hear more on the details of this in the second section of talks, but for now I really want to bring to the front of everyone's minds that every time we press go on an analysis, we are burning fossil fuels. Every time we press go on an analysis, we are heating the planet. And every time we press go on an analysis, we are actually reducing our future ability to conduct science because we are making our planet and human society unstable. Now, we do actually know what we need to do about this. The Intergovernmental Panel on Climate Change tell us that if we're to have even a 50% chance of limiting warming to 1.5 or 2 Celsius, this requires rapid, deep, and in most cases, immediate greenhouse gas reductions. And that includes emissions from our scientific analyses. You'll often hear the phrase net zero bandied about, but what does that actually mean? It means for us to limit warming to 1.5 or 2 Celsius, we need to reduce greenhouse gas emissions back to pre-industrial levels. But there are some sectors where this is going to be really hard, where there isn't a technical or behaviour change solution. So we'll have to find ways of mitigating those continuing emissions. And that's where the concept of offsetting for net zero comes from. And I want to explain this because colleagues will sometimes say to us, oh, but we can just plant trees, right? And then we don't need to change anything. No, unfortunately not. So the concept of offsetting is that after we've reduced emissions as much as we can, there'll still be some residual emissions that are really difficult to reduce. So to get our overall levels of greenhouse emissions down to zero, we'll have to suck up that carbon out of the atmosphere. And one great natural way of doing this is by planting trees or by nature restoration. However, there simply isn't enough land on the planet to do this. We calculated that for the Organisation for Human Brain Mapping 2019 conference, we would have needed to plant 200,000 trees to offset the emissions from the attendees flying to attend that conference. And unfortunately, we can't rely on man-made offsets, so-called negative emissions technologies, because they do not yet exist. So this means we can't rely on offsetting to get to net zero, and we must reduce energy in real time. And we hit a further snag that renewable energy is in fact limited. And that's because there's only so much physical infrastructure that can be built. And remember, there'll be ecosystem impacts of building that infrastructure. And of course, every other section of society is also looking to decarbonise. So that means we'll have a limited amount of energy to go around, and every other section of society will be looking to use it. Therefore, we need to pull every single possible lever that we can to reduce energy consumption, and we need to do it now. And with the advice that you'll pick up today, hopefully we'll go away with a toolkit to reduce energy of our analyses, at least to a degree. But I'd like to plant the seed in everyone's minds that beyond today, I think as a field, we also need to have a serious conversation about demand management. And by that, I mean as having a conversation about reducing the amount of science that we're doing. Because if we want to get to absolute emissions, not net zero, absolute zero, we need to think about the volume of science we're conducting. Can we afford to continue in the way we have been, knowing that it will limit our ability and that of future scientists to work safely in the coming decades? But today, in the short term, the good news is there are potentially lots of things that we can do to reduce energy consumption of our analysis. But how to choose from all those things? Well, I'd like to suggest that we first start with high impact actions that could substantially reduce our emissions, but that are relatively low effort. And hopefully lots of the suggestions you'll hear today are in that category. We do need to make this as easy as possible for our colleagues who aren't here today, who are low on time and low on headspace. We need to give them the easy solutions. So through today, let's look to identify those high impact but lower effort actions that we can take. I also want to emphasise that what you do as an individual really does make a difference. Because sometimes I hear colleagues say, oh, what we do doesn't matter, it's up to the government. And yes, we urgently need governments to legislate, but they don't have a clue about our work. They don't have a clue that our analyses are burning fossil fuels. And in fact, the people who have the deepest insight into our work and who are therefore best placed to tackle carbon emissions arising from it, that's us. Those of us actually doing the research, actually running the analyses. It's up to us because the government, even funders, don't understand our work as well as we do. I feel we also have a moral duty as practicing professional scientists to take responsibility for our own professional footprints. And finally, I think there's also a really important influence on social norms that we can't underestimate. In this paper last year, we set out 5 main domains in which scientists could take action. And here today, we're focusing on actions in our own research, specifically computing. But I really want to emphasise how taking action at one level affects what goes on at other levels too. Because when you change how you're analysing data and when you tell colleagues about it, it changes perceptions amongst those colleagues in your department, amongst colleagues in your university or institution. It's socially norms that scientists, and not just climate scientists, all of us care about this and that will stand up and do something. And that creates a very powerful social mandate for change that funders, that institutions and that governments can't ignore. And I want to emphasise that I think the single most important thing that any of us here today could do, regardless of our computing activities, is to talk about it. because that's how individual actions percolate and change society, and that's what we're doing here today. So thank you so much for giving up your time to be here, and I hope that the next sessions give you food for thought and some specific actions that you can consider. I'll take some short clarification questions in a moment, and then I'll hand over to Gabby, who'll zoom out for the institution and funder level view, because critically we do need to come together as collective groups of individuals to make these changes. Thank you.